right, so I don't want to talk about how to break down the lit peptide. I want to talk about how to build it up. So let's talk about solid phase peptide synthesis. The key to that quiz was already posted because it was the quiz that I posted as an example. Same as last year. So let's assume that we want to make our little peptide. Which has leucine, isoleucine, and threonine in there. Obviously, I put those two in there because they're the two that have chiral centers in the side chain. So this one is the S chiral center in the side chain, and that one is the R chiral center. They're the only two that have additional chiral centers besides the alpha carbon. So let's say we wanted to make that. And we're going to start with our polystyrene resin, which I'll just abbreviate PS, cross-linked with divinylbenzene. And then on some of the benzene rings, we've chloromethylated it. Right? So we went from our plain old polystyrene and we chloromethylated this with chloromethyl-methyl ether and some Lewis acid. I can't remember if the textbook uses aluminum chloride or stannate chloride, but it doesn't really matter. But chloromethylation, that's a plain old electrophilic aromatic substitution. Peptides are almost always built from the C terminus to the N terminus. So the first amino acid that we're going to want to attach to that is the C terminal amino acid, which is this one. Because we always write it from N terminus to C terminus. So we're going to start with threonine. And we need to start with the right stereoisomer of theanine. So we need this to be an R chiral center. There's a CH3 group here. Right, so that's the R stereocenter. S here, R there, hopefully. Assuming I drew that correctly. So choice 1, choice 2, choice 3. Problem is, we've got, in addition to this nucleophile, which is what we want to displace the chloride with, we also have the oxygen lone pair on the OH group, and we also have the NH3 plus. And we always have residue or equilibrium where we have some of the free amine as well. Free amine is going to be what we need. And I'll stop showing the stereochemistry on that R stereocenter. So what do we need to do to protect it? We actually have two things we need to protect. We need to protect the NH2 group. We also need to protect the OH group. What protecting groups do we know that we can use for those two functional groups? What's that? So we're going to protect the amine group, but what are we going to protect it with? Right? We have those three protecting groups. We have BOC, we have FMOC, we have CBZ. And which one we choose might depend on what we're going to use to protect the OH group. One of the most common protecting groups for alcohols is that with isobutene and HF and convert that into the tert-butyl ether. And then we know that we can cleave that tert-butyl ether later with acid. But if we're going to use that, the T-butyl protecting group for the alcohol, we had better not use Bach for the NH2 group, right? Because then we're going to remove them both when we treat it with the acid to remove the Bach group. This group will also fall off, and that'll be problematic. So we need orthogonal protection here. We need to protect the nitrogen with something that can be removed without removing the protecting group from the oxygen. And it would be really nice if we also could remove the protecting group from the oxygen without deprotecting the nitrogen. That's stolen from math. The orthogonal protection means we've got the ability to remove one in the presence of the other. So the logical protecting group for this is one that is removed under basic conditions, so that we don't have to worry about removing the wrong protecting group at the wrong time. And the protecting group that we usually use for that is 9-fluorinomethylchloroformate to make the FMOC group. So nitrogen is going to come in here. It's going to attack this carbonyl group, pushing a pair of electrons onto oxygen, and then in the second step, that'll come back down in to gap out the chloride. We'll have a proton transfer step, and we will end up with our FMOC protecting group. It'll look like that, right? So we've protected the N-terminus with a group that's base labile, but acid stable. And now we can treat that alcohol with the isobutene and the HF. The FMOC group will stay attached. And we'll make the tert-butyl ether. So we now have something that's acid labile but base stable. This is what we're going to treat our functionalized resin with. So we'll use a mild base to convert that into the anion, and then we'll simply do an SN2 displacement to attach that to the resin. So we have our polystyrene resin, and then we have our amino group attached. Now we have to actually show the protective group. So there's our 9-fluorinomethylchloroformate. Here's the fluorinomethylmethyl part. Or sorry, 9-fluorinomethylmethyl protective group, right? So here's the 9-fluorine part, the methyl, and the oxycarbonyl. So we're attached to the solid phase. That's the first step. That's an SN2 reaction. Now we need to take off this protecting group so that we free up the amine. The reagent for that is piperidine. We're going to do this elimination reaction, beta elimination. polystyrene. So many atoms. We get our dibenzyl fulvene out when we get this, which spontaneously decomposes to generate CO2. And after a proton transfer, we're going to end up with our free amine. Make sure that hydrogen doesn't look like it's attached to the methyl group. So we have our first amino acid linked to our polystyrene. And FMOC is pretty good for solid phase synthesis, less appealing for solution phase synthesis because that's a pretty large, bulky molecule, and it also reacts with additional piperidine to form an amine because of the stability of the anions. So we'll have some byproducts in there that in solution can be problematic to get rid of, kind of like the triphenylphosphine in the Wittig reaction. But on solid phase synthesis, since this is attached to a bead, you can wash it with a lot of solvent. You basically pour this polystyrene bead into a chromatography column, and then you run your reagents down the chromatography column. All the byproducts are easily washed away. So we can use a significant excess of piperidine. We don't have to worry about these byproducts. They'll be washed away nicely. You look perplexed. Did you have a question? Did I mess something up? It's not unlikely that I'll leave atoms out. So there are two chiral centers, which I'm not showing the.
Wait, so you just like add another one? I'm confused.
What?
Where you move, like you use the piperidine for the first one, but then where the heck are you going?
So wait, I forgot to put my hydrogen in.
Like why? Like what are the two?
Right now I've just
I
got.
missed an arrow.
Right now I've just got theory attached. So CO2 falls off to get the N minus, and then I got a protonate to make the NH2.
Step to the I missed the arrow to the O. I'm like, how do you have two different things? I don't understand.
Sorry. Yep.
It's fine.
So, yeah. Sometimes you draw the carbamic acid as an intermediate and then have an intramolecular proton transfer. But in this case, since we're under basic conditions, the carbamic acid is probably not an intermediate. It probably just spits out CO2. I could have showed it for spitting out CO2 all in one step. Not actually certain if that's multiple steps. So now we've got this. And now comes the crux of the problem with peptide
There's no
synthesis.
erase it all yet.
I'm going to stop here
Okay.
and leave that part. So now we've got our polymer, polystyrene. We've got attached it to our AR group. And we've got our one amino acid with its little protecting group on the alcohol and an NH2. We're going to protect the or the N terminus of the isoleucine with exactly the same protecting group. So we're also going to have the carboxylate ion with an FMAR protection on there. And our isoleucine, which is this secondary butyl group attached. And this should be the S stereocenter for isoleucine, assuming I've showed that correctly. 1, 2, 3. Sorry. 1, 2, 3. So I got that backwards. That's the R stereocenter. Yep, yes. So the question is, how are we going to get this nitrogen to attack that carbon? And we can't do it while this carboxylate is still negatively charged. This is an unreacted carbonyl group. Are you done with this? So the question is, how do we activate a carboxylate and turn it into something that will react with a nucleophilic lone pair on the amine? If we were working with a simple alkyl group, and we had a carboxylate like that, and we wanted to react this with some kind of amine, what we would probably do is just convert that to the acid chloride. So we could treat this with PCl5 to make the acid chloride. And then we could treat that with the amine and make our amine. Right, so this would be nucleophilic acyl substitution here. And this is nucleophilic acyl substitution. Carbon, but after an SN2 reaction with PCl5. So we would take our PCl5, we would do this, take out a chloride, and then we do a second step. That's great, right? When you're working with simple things and you don't have to worry about the fact that you're liberating a ton of HCl in that step and some HCl in that step. But in our case, it's likely that all the rest of the peptide is going to get decomposed by that. So we need a milder way of activating this carboxylate group that doesn't involve the formation of HCl. And the reagent that we use for that is dicyclohexyl carbodiimide. It's got a very electrophilic carbon, because you've got two electron withdrawing groups pulling that electron density away from the carbon. So that carbon is going to get attacked pretty readily by the C-terminus of the amino acid. So let's simplify this a little bit. Let's just write it as FMOC NH CHR CO O minus. And what we're going to do is activate this terminus. This R group is the sec-butyl. Sometimes you'll actually see people abbreviating the cyclohexyl ring, just writing it as CY for cyclohexyl. I'll just show the ring. So we would expect this lone pair to attack that carbon, push a pair of electrons out onto nitrogen. That should be a pretty favorable reaction. There's always going to be some of the C-terminal amino acid in there with the hydrogen on it, along with the anion. So there's always a source of protons. I'm just going to say BH plus, the base. So then we're going to protonate that. So many atoms. Biological molecules are annoying that way. So we've got our FMOC H, our CHR, our carboxy terminus. And I've actually rotated it because I want to focus on this group right here, because that should look anhydride-like to you. It's not an anhydride because one of those double bonds is a CN double bond instead of a CO double bond, but it looks like an anhydride.
Did you lose that butyl thing? Is that stay or go?
The sec butyl is this R group
Oh, never mind.
in parentheses.
I thought that was like a bond to it.
No, that's saying that the R is that sec butyl group with the S stereocenter. Right, so what we've done is we've activated it. This is a nucleophilic acyl addition reaction. Where step 1 is just the nucleophilic attack. And then step 2 is the protonation of the nitrogen to add the elements of the carboxylic acid across that bond. So we've added the hydrogen to this nitrogen and the carboxyl to there. So basically what we've done is added this piece across the CN bond. This is now a good leaving group because if this comes off as O-, we'll be able to resonate it onto the nitrogen. So now we actually have a reactive carbonyl, where before we had an unreactive carbonyl. This can get attacked by that load pair. So we need to figure out how to draw the thing. That's the problem. So like this. FMOC NHCHR, our carbonyl group. This is our mixed anhydride here that's going to get attacked. Now we embark on the process of drawing way too many atoms. Standard nucleophilic acyl substitution. First a nucleophilic attack, then a loss of a leaving group. polystyrene with our amino acid attached. And then we have our ethyl group out here. I won't actually redraw that whole thing without that proton on there, right? Step 3 is always going to be the proton transfer. And that will make our new amide bond. So we've done a nucleophilic acyl addition across the carbon-nitrogen double bond of the dicyclohexyl carbodiimide to make the mixed anhydride, and then we're doing a nucleophilic acyl substitution at the carbonyl of the protected amino acid. And you'll see dicyclohexyl carbodiimide again in group 1's presentation because it's also an activating agent for phosphate. If you want phosphate to get attacked, right, phosphate is an anion, it's an unreactive phosphorus, but by reacting it with dicyclohexyl carbodiimide, you can make a mixed phosphorus carbon anhydride. That will then render that phosphorus attackable. So now we've got our 2 amino acids attached to our polystyrene. We're just going to do it again, right? We're going to treat it with piperidine, and that's going to remove that FMOC group. We'll have our polystyrene. We've got our carboxy terminus attached with our protected threonine. And now we've got our new amide bond. We've just made our new amide bond. And that takes all. Hopefully I didn't mess up. Got all the same atoms present that we used to have. Maybe. I flipped it.
Did you do something?
I turned this to make it an angle. Right, so I had it pointing up here.
Oh, you removed the.
This is gone. Right, piperidine took this off, liberated CH2 and generated the NH2+. I didn't show the intermediate after the proton transfer because why draw things more times than we have to?
On my exam, mechanism left with the instructor.
What's that?
So can I do that on my exam? Mechanism left as an exercise for the instructor?
No, but you can say PT and not show every individual proton transfer.
I think I would like it better if I left it to you.
You can if you want, but then I'll get the points too. So that's fine. I mean, I can use some extra points. So basically, we've now got a dipeptide. We've got threonine and we've got isoleucine. All we need to do is treat this with DCC and then treat it with the FMOC protected leucine. And leucine is the isobutyl group as opposed to the sec-butyl group. That'll put our leucine on there. So we'll have our polystyrene. Have our butyl group on there. Have our isoleucine on there. And have our regular leucine on there. Oops. Probably be a good idea if I put that carbonyl in the right spot. Also be a good idea if I didn't run out of space. I have run out of space. So there's our fully prepared. There's our T, there's our I, there's our L with our sec-butyl chain. So now we have a problem. We have to disconnect this. We have to take this off the solid phase. So basically what we're trying to do is cleave this bond. There are various ways to do that. That is a benzyl ether. Which means it could be hydrogenated. If you add H2 gas, you'll add hydrogen across that carbon-oxygen bond and make a methyl group here and liberate that. That's one way to remove it. But you can also exploit the fact that SN2 reactions occur pretty rapidly at benzylic positions. So if you treat this with an acid so that you protonate this carbonyl group, you can then do an SN2 reaction. And an acid that's often used for that is the same acid that we use to put this group on in the first place. So we can deprotect the alcohol and remove it from the solid phase in a single step by using HF. It will deprotect the alcohol and it will cleave it from the solid support. And that's an SN2 reaction. So without showing all the atoms, because there are too damn many of them, what we're looking at here this NHR, that's the rest of the peptide. Is we're looking at a protonated carbonyl group where fluoride ion will come in and push that out. Terminus, and at the same time chop off this tert-butyl group. So we just regenerated the carboxy terminus by chopping that off. The last step would be to treat it with piperidine again to take off the F-mark group from the N-terminal amino acid. So it's a sequence of treating it with piperidine to deprotect the F-mark group, activating that with dicyclohexyl carbodiimide, adding your next free N-terminal amino acid, going from there. Right, so we're activating this guy, adding it to the N-terminus, deprotecting, activating, adding to the N-terminus, deprotecting, activating. And every time at every individual step, you're going to wash away all your byproducts because your compound of interest stayed attached to the support and all your byproducts are still in solution. Lots and lots and lots of atoms, and if you were trying to show this on an exam, you would want to make liberal use of R to represent the pieces of the molecule that aren't actually necessary as part of the reaction you're showing, but are still there. Just as long as you make it really clear what you mean by R. Right? You don't want to have to draw every single atom at every single step, when what you're focusing on is these two arrows. Yes? Solid phase peptide synthesis? It'll take some review, you'll have to look it over. You can use the box protecting group here as long as there's nothing acid sensitive in your side chains. So if you didn't have that alcohol, right, if we didn't have this T-butyl group here, it would be perfectly reasonable to use the box protecting group instead. It is not common on solid phase to use CBZ because hydrogenating a solid phase is not convenient. It's either the acid or the base sensitive protecting group that's usually used. The Bach is probably more common because from an atom economy standpoint, the FMOC is big and heavy and a lot of atoms you're throwing away, and so that's money. But you can't use Bach when there's acid sensitive protecting groups on your side chains, which basically means if you've got a leucine, or if you've got a threonine or a tyrosine or a serine, where you have those alcohols in the side chain, you're typically going to use FMOC instead. Let's take a break, and then we will talk about sugars for a little bit. Next Tuesday we have your presentations. I will probably try to be in my office pretty much all day on Monday for last minute questions, and I can come in on the weekend. If you're working on your project and you need me to come in and help, just email me. It would be possible for me to come in on the weekend with a little bit of notice if I need to. Obviously, I'll have office hours tonight too. There's no quiz on Tuesday. We're just going to do the presentations. Yeah, give me a sec. Let me